Welcome back to our second Unit 2 video regarding lipids. In this video, we're going to discuss cholesterol and trans fats. So let's begin. Cholesterol is what you would, if you could see it in a vat, it would be a soft, waxy substance that is in your bloodstream. If I had a large container of it, it would literally look like a yellowy cottage cheese waxy substance. Kind of disgusting sounding, right? Especially if you eat cottage cheese. But that's what it is. It is a soft, waxy substance. Now, if you've heard of cholesterol before, your probably first instinct is to think that it is something bad for you, which it is, in excess. All right? But just like everything in life, too much of something is not a good thing. So cholesterol does have a very important function, actually functions within your body. All right, some of those would be, all right, used to form cell membranes and create hormones, such as testosterone and estrogen. There are many, many more functions besides those two, but those are the two that I want you to at least focus on. All right, so all of your cell membranes are made up of both regular lipids, in particular phospholipids, and they will also have some cholesterol mixed in. Also, cholesterol is pretty much the starting point right here, so I'm pointing to the overall structure for cholesterol. You can use this and just do a couple tweaks to modify it into a hormone such as testosterone or estrogen. Now, this structure here obviously is much different than anything else we've seen before. It looks nothing like a triglyceride that we went over in the last lecture video. So why is this a lipid? Well, it fits both the category of lipids as well as what we call steroids. Now, it's a lipid because overall the molecule is still held together by a nonpolar bond, so it is not soluble in water, just like any other fat is. So it would sink or float depending upon the amount and density of the molecule. In this instance, a large amount of cholesterol would actually sink to the bottom of a flask. Now, it is also considered a steroid because it has this very specific structure that you see up here. Steroids are always characterized by 4 carbon rings that are fused together. There's not a bond linking them together, they're actually fused. So each ring you see and each point would represent a carbon atom. And that they will always have one fatty acid tail that is attached to them. Now that fatty acid tail may be to the right, to the left, facing down or up, but all steroids have a classic structure of 4 carbon rings fused with a fatty acid tail. Alright, so that structure, it is a lipid because it's nonpolar and doesn't dissolve, but since it has this unique structure, we also call it a steroid. Now, cholesterol, as I mentioned, has many functions in your body. The one key function that we're going to focus on, especially next unit, is its importance in cell structure formation, particularly the cell membrane. Now, the cell membrane is made up of phospholipids, which are very similar to triglycerides. They just have 2 fatty acid tails instead of 3. But these fats would make your membranes very, very flexible. So if you put a couple cholesterol molecules between every other phospholipid, what that does is it actually stiffens up your membrane. So if 2 cells collide, they're not just going to explode like water balloons, right? It'll actually stiffen them up, decrease their flexibility, but not to the point where they're going to be too rigid and stiff. All animals have cholesterol in their cell membranes. Plants do not because they have a cell wall that surrounds their cell membranes, which is made of cellulose. So the problem moving forward now is this. If you make all the cholesterol that you need in your body, and your liver is actually responsible for it, what happens when you eat any product that comes from animals? Either meat directly or any type of baked good that's using things like butter or oil that has been removed from animal products, you're now actually consuming additional cholesterol that your body was not meant to have. So what does your body do? It has a way to try to manage those cholesterol levels in your blood, and it's going to employ the help of what we call lipoproteins. These are going to be proteins whose sole responsibility is now to transport and collect cholesterol in your blood and bring it from cell to cell. The problem is, of the two types, LDL and HDL, which each stand for either low-density lipoprotein or high-density lipoprotein, one of them is like a good Uber driver or taxi cab driver, while the other is going to be bad. Now, which one is which? LDL, low-density lipoprotein, is what we're going to refer to as the bad cholesterol or the bad Uber driver. The reason why it's bad is, it is like a criminal over here, or in other words, if you ever heard of a kleptomaniac. A kleptomaniac is someone who just has to steal, they have to take, they have to hoard, they can't help themselves. So LDL, when it sees cholesterol in your blood, picks it up, but doesn't really deliver it where it needs to go. It just hoards it and holds it in the bloodstream. Unfortunately, over time, as you eat more cholesterol, you make more LDL. As you make more LDL, the overall cholesterol in your bloodstream increases, which can lead to, over time, blockages that we call plaque. And this plaque, eventually, if it seals up your arteries altogether, stops the blood flow in the location where the blockage has occurred, which leads to either a stroke in your brain or a heart attack if it's any arteries that are leading directly back to your heart, or away from your heart, I should say. So LDL is bad. HDL is the good cholesterol. Now, the reason why it's good, or it's a good Uber driver, it's going to pick you up and take you directly to where you want to go, and it's going to deliver you there as quickly as possible. Now, where is HDL going to deliver cholesterol once it picks it up? To your liver. HDL recognizes there's cholesterol in your blood. Rather than grabbing it and just holding it so blockages can occur over time, it removes it, brings it to your liver destroys it, which is going to reduce the speed at which you're going to get blockages over the course of your life. So this is one of the cases where you do not want to have homeostasis between LDL and HDL levels. You want to have a much higher level of HDL, so you're always removing more cholesterol from your blood to break it down, rather than keeping additional cholesterol in your blood, which can lead to blockages and heart disease over time. All right, that's the key. The second type of fat, to finish out our lecture here, is going to be what we refer to as trans fats, or you might hear them referred to as hydrogenated oils. So have a look out on your nutritional labels for anything that says trans fat, or even if it says 0 grams, look at your ingredients, and if it says anything about oils being hydrogenated or partially hydrogenated, you want to avoid them at all costs. Now, what are these? These are oils, all right, cooking oils, like vegetable oil, that have been turned into a solid form. Now, what a scientist would do is they would take an oil and they would boil hydrogen in a vacuum through the oil. That hydrogen breaks the double bond. See over here, there's a double bond that's kinking this fatty acid, which would be a liquid. It would break that double bond and theoretically straighten out the fatty acid, where it now becomes solid at room temperature. Now, why would you want to do that? Well, oils don't have a long shelf life. They don't last very long before they start to go bad. Plus, they're not as heat resistant over time. If you keep using the oil to fry, say, French fries at McDonald's, halfway through the day, that oil starts to break down because of the heat, and you've got to drain it and replace it. People don't want to do that, especially in the food industry. So some mad scientists a couple decades ago figured out, let's take an oil, which people normally think are healthier for you, make them become solid, which is going to extend their shelf life and make them more heat resistant. Maybe now I don't have to replace the oil for a couple days in my fryer. It sounds kind of gross, right? The problem is, this process over here where I'm pointing to, you want to break the bond and make it look exactly like saturated fat. But what can happen is, that doesn't exactly happen. You might make it look like this. See how the molecule has straightened out, but it still has, right here, double bonds intact? Well, you're going to take the oil and you're going to solidify it, because you're going to kind of make the molecule become more dense since they can get closer together. But the problem is you still have that double bond, which is going to confuse your body, and I'll explain that in a moment. So you don't have to write any of this down, but you're going to put oil in a vat, remove the air, pump hydrogen through it, and that process is going to do this over here. Break the double bonds, add hydrogen, so you want it to look like a saturated fat down here. It looks exactly like it, right? Even though you've now hydrogenated it. The issue is as you try to do it more and more. So you take an oil, and you try to break more and more double bonds to add hydrogen, so it's going to get harder and harder to the point where you would make it straight up vegetable shortening. So any margarine or like Crisco shortening in your house is a trans fat or a hydrogenated oil. That's not going to be good for you. The reason why it's not going to be good for you is what you're trying to do is this. All right, you're trying to take an oil, break the double bond, add hydrogen so the shape looks just like a saturated fat. Now, saturated fat isn't good for you, but your body recognizes what a saturated fat is, so it knows how to handle it. When you take an oil again, see here it is. This will be a monounsaturated cooking oil, like vegetable oil. Break that double bond. This is what you want. But that doesn't always happen. Maybe it happens 50% of the time. The other 50% of the oil is being chemically altered to look like this. See how the fatty acid or the oil has now straightened out? So it's going to be solid, but the issue is this double bond wasn't broken, and what you've done is you would want to have these two hydrogens on the same side, right? But now what you've done is you chemically modified it that one of the hydrogens has flipped sides and now it looks like this. This is called the trans configuration. That it's almost like if you think of transatlantic, go from one side of the Atlantic Ocean to the other. They're on opposite sides of the double bond. This is not a natural state for a fat. Your body doesn't know what this is. Remember my phrase, shape dictates function. When your body sees this, it freaks out. It doesn't know if it's an oil, an unsaturated fat, or a saturated fat. So, just like you would, if I were to give you a test tomorrow on cell respiration, I've never taught you a thing about it, you'd freak out and overreact and maybe have an anxiety attack. That's exactly what your body does. When your body sees this configuration right here, so this is a natural unsaturated oil, you want to break that double bond, add hydrogen so it's perfectly straight. But now, if this happens by accident, where you don't break the bond and you just change the orientation of the hydrogens, your body, in essence, thinks that this molecule, it takes a guess, and it thinks it's cholesterol. And if it thinks it's cholesterol, your body makes more LDL. And if you make more LDL, you pick up more cholesterol in your blood, which can increase the rate at which your arteries start to clog up, you form plaque, and lead you to have a heart attack eventually quicker than you ever would before. On top of it, these fatty acids, your body doesn't know what to do with them, can lead to the development of some cancers on top of it. So any type of trans fat or any type of thing that's called partially or fully hydrogenated oils, this is what you're getting sometimes. A mistake where your body doesn't know what it is, you overreact, and you're going to have increased heart disease as well as possibly cancers over your lifespan. All this came out to play a couple decades ago where someone, a woman, if I go back real fast here, every night she would like to eat Oreos. And she would eat a lot of Oreos. I'm talking 1 or 2 full sleeves out of a package of Oreos. That led to her having numerous heart attacks over time. When the doctors looked into it, they examined that she ate Oreos, found out that there was something called hydrogenated oils in them, and they discovered that that's what this was leading to, is heart disease as well as eventually cancers. So now you need to be made aware of if you're actually consuming any type of trans fat or hydrogenated oils because they are dangerous for you. Any questions? Make sure that you ask me during our live lecture. Thank you very much.